Hi, I'm Ben Leedom. I know some of you. Met some of you over the last couple of days. I'm going to be telling you today about a language called Rebar. First, I want to talk about our giants are female. I want to talk about Emmy Noether. Emmy Noether was a mathematician around the turn of the 20th century. She made a lot of contributions to fields like abstract algebra. She did a lot of development around some of the basic structures we know today as like rings, fields, and algebras. But she also made contributions to theoretical physics, and in particular, what's called Noether's Theorem, which is this really neat result that like anytime you have some sort of physical system symmetry or some kind of conservation, that there's a correspondence between those two. And that applies not just to classical things like conservation of energy and momentum, but also to some of the things that have come up in like more modern physics. So it's, yeah. Okay, so let's get a few things out of the way first. I'm not going to try to teach you how to all the ins and outs of programming in Rebar. Rebar is a graphical data flow language. We're going to see how it's kind of looks structurally similar to G and functions somewhat differently to it. If programming in it is something that you're interested in, then I can definitely try to provide documentation and things like that outside of this presentation. Although right now the documentation mostly looks like, hey Ben, how does this work? And then the answer is usually like, oh, I think there's a Twitter thread for that. Really, more what I want to do is talk about, what are the things that make Rebar different from G? What are the things I think make it interesting? And hopefully give you more of a flavor of like, why is this something I would want to use, or what's interesting about it? I also want to say that this is purely a personal project. This is not something that National Instruments is working on or investing in or releasing. It's also being released as open source. So there's a GitHub link, you can go there, which means not only that is it free for you, the community, to download and look at, but also to contribute to. So if that's something you're interested in. The main reason I want to show it to you today is, for you as the members of the, graphical language community, the graphical programmers, to try it out and let me know what you think. Let me know if you have any feedback, or even just if it, seeing this sparks any ideas or concepts in your head. Just a little bit about me. I've worked at National Instruments on the LabVIEW NXG development team for about 11 years now. I worked on things such as the front panel editor, and then later the code conversion utility, and more recently the team that's working on applications and libraries, which has a lot better graphic design. I also want to say a little bit about the title of this presentation. So what Rust can teach G. Rust, you may or may not have heard of, is a relatively recent systems language that originally came out of Mozilla. And like other systems languages like C and C++, it's geared around efficiency, but its main focus or claim is that it can also enable things like safe concurrency. And that sort of dovetails pretty neatly with the aims of G and providing a graphical data flow environment. Also, unlike traditional systems languages like C and C++, it has a lot of influences from various functional languages. But the really unique idea that, no pun intended, that it brought to the language space is this concept of ownership and borrowing. And we're going to see what that means shortly here. So just to get the basics out of the way, Rebar has a graphical syntax similar to G. So there are nodes that represent computations or functions. There are wires that represent transferring values between computations. There can be nodes that contain nested diagrams that can contain their own nodes, and those are structures, and structures can move things in and out of them using water nodes. And nodes run in what's called data flow order, so if a node has to wait for all of its inputs to be available, which means all of its upstream nodes have to have run. And if two nodes have no data flow connection between them, then they're considered to be able to run in parallel. So far, everything I said is also true about G. So let's look at some fundamental ways in which Rebar is different from G. So G has this distinction between wires as carriers of values and then other things that represent containers of values. So here's a simple example of taking some constant values and then doing some math with them, passing the values along wires, and then passing the final result into an accessor. But some examples of things that contain values in G are local and global variables, although NextGen doesn't have globals. But this is an example of accessing the same variable multiple times in sequence, and so each of these accesses is to the same place or container of values. And then things like shift registers and feedback nodes in a loop also serve as a container of a value, something that you can read a value out of and write a value into. And they're a little bit more limited in that you can only read to them and write to them once in a loop. And then I also tend to consider the left and right nodes on an in-place element structure to be a similar sort of value container, in that you're setting up a temporary place where you're reading the subparts of a value, and then you're writing something back to it, but you're temporarily considering the left and the right to be the same thing for the purposes of modifying it in place. In Rebar, wires directly represent variables. Wires identify variables. And one of the first things we can see with Rebar syntax is that wires have this, oh good, it does show up. Wires have this sort of halo or border around them that indicates what kind of variable they are associated with. Not just the data type, but whether the variable is mutable, its value can change or not. And so the little diagonal hashes represent a variable that's mutable. Wires can relate to variables and to output terminals in one of two ways. An output terminal can either begin a new variable, and so here there's an example of an output terminal says a new variable begins here and its initial value is whatever value came out of this output terminal. Or otherwise, a variable can be continued at an output terminal, which means there was a variable before this node, and it went into the node did something with it, and now there's another wire coming out of the node representing the self-same variable. And this is accomplished with what are called pass-through terminals, which are pairs of an input and an output, where they're defined to say the two wires connected to these terminals are the same thing. And so you combine these two notions, and what you get is variables existing as a sequence of wires, connecting two or more different computations on a diagram. And so in this example, there are 5 wires, but there are 3 distinct variables. The sequence across the top is all passing through and using the same variable in place, and it's starting with one value and accumulating and multiplying different values onto it before passing it to output. And then the 2 on the bottom are their own variables. And so we can also think of this as, you want to think of transforming what this means into G terms. If you think of every place where we begin or initialize or define a new variable as defining or creating a new data value reference, and then of every node as existing within its own in-place element structure that dereferences all the DVRs you're passing around and does things internally with the dereference values and then passes them back out. And then at the places where we'll see where the endpoints of the variable exist, that you're cleaning up the DVRs, that starts to approach sort of what's actually going on in Rebar. Now, this is not actually what the Rebar compiler does. This is really more just an illustrative guide. Now, I think the main thing to take away from this, this concept of wires as variables, is that what it enables is a more flexible notion of what the lifetime of a variable is. So in G, in all the value container examples I cited, a variable either exists sort of like within the confines of a particular structure, like shift registers are sort of bound to the structure that they're on either side of, unless they're uninitialized, and that's a different story. Or things like a local variable will sort of, their lifetime is identified with the VI that they sit inside. So across all calls to that VI, you have a variable sitting there going along with it. Or with a global variable, the lifetime is associated with sort of the whole hierarchy. Instead, by saying that wires themselves identify variables, we can point to any two places on a diagram and say, between these 2 points is the scope or the dynamic extent of some variable. And the particularly important thing that we'll be able to build on later that we'll see is that for any variable we can point to a start point and an end point for that variable. Okay, so that is kind of the basic fundamental distinction between how G thinks about wires and how Rebar thinks about wires. So now let's look at something a little bit more advanced. And this is going to be RAI and ownership. And to introduce this, I want to talk a little bit about how G handles things like resources. And I'm using resource as a stand-in for something that lets you do something useful with a computer, like a handle to a file or to a network stream or to a device. For those 3 things and for other types, G has what are called refnums or references. And these are sort of handle-like types that refer to something in a table that's maintained by the LabVIEW runtime, and the LabVIEW runtime tracks what each refnum is referencing. But refnums suffer from at least 2 different kinds of problems, and they've already been kind of alluded to in some of the other presentations today. One is that they can leak, and a leak is just where you acquire a resource and get a refnum to it, and then you forget to free it. And then the other problem is use after free. And this is a bit of a contrived example, but use after free is any time you free a refnum, but you also save off some reference to it someplace that allows you to use it later or in parallel, such that the usage happens after it was freed. And in both of these cases, the LabVIEW runtime will kind of save you from what happens here. In the leak case, eventually the runtime will notice, hey, the VI that's holding onto this resource is about to go away and nobody's using it, so I'm just going to free it. But that may happen long after the VI has last run. And then with use after free, the compiled code and the runtime will insert a check basically on every usage of the reference to say, is this reference still referring to something valid? And if not, then whatever you were doing will immediately return an error and fail. The point is, though, that these things are things that the LabVIEW runtime has to support. The compiler cannot. The compiler, because of the rules of G, does not have enough information to know, in general, whether you're using refnums safely. That is, whether you're always freeing them when you should and then not using them after that. So one of the things that other languages have done to start to work around problems like this is what's called resource acquisition as initialization. And this name is given to it in computer science literature and in some of the languages like C++ that provide this feature. But probably a better name for this concept is scoped resources. And the basic idea is that when you perform some operation that's going to require a resource, like opening a file or whatever, you call a function and then you assign or bind the result of that function to some variable. So that's the acquisition as initialization part. You're acquiring something and then initializing something at the same time. But then the other half of this is that when the variable that you initialized goes out of scope, that the compiler will automatically insert a call to something like a destructor, something associated with that type that frees up the resource. And so this is how you start to get around the problem of leaks, is by letting the compiler take care of it for you, by basically saying anything you declare automatically within the scope of a function, once that function or that scope ends, we're just going to automatically free whatever you were using. Now, C++ provides this feature, but it also has other features that let you do things like creating a pointer or a reference to a resource within the scope where it exists, and then leaking that pointer or reference outside the scope and then trying to use it later. And that's still a use after free error. And the C++ compiler can't really prevent that. What Rust does is it takes resource acquisition as initialization to another level and gives it a new name called ownership. And the new idea with ownership is that when you have a variable that got whatever resource you required, within the scope that variable exists, it is the unique owner of that resource, which means that what the compiler is going to do is enforce that within that scope, any other reference or thing you use or create that references that resource is not allowed to outlive the scope of the variable. So that by the time the variable scope ends, it is guaranteed to be the last thing that knows about that resource, so it is always safe to free it, and we prevent anybody from using it afterwards. So this is taking something that prevents leaks and also extending it to prevent use after free. We're guaranteeing that not only are we going to always free everything when it's appropriate, but after that point, we are not allowed to use that thing again. So ownership is the main concept that I tried to import into Rebar. And this is an example where we open a file handle, and then we make sure that there wasn't an error, that it's a real thing, and we can ignore that part. But then after we open it, we do some sequential operations to the file handle, like writing strings to it. And going back to what wires as variables give us, we can point to there's a beginning point for this variable, which is where we acquire the file handle, and then there's an endpoint at the end of the sequence of wires, and it's at that endpoint where the compiler can automatically say, okay, you're no longer using this. This is where the variable ends, so this is where I'm going to insert the free, or the release. So, by bringing in ownership, we've sort of eliminated the problems, or at least the two problems that refnums have, where you can either keep things alive longer than they should, or try to use them after they've already gone away. There's another problem that refnums have historically had, and that's that it's rather difficult to create new ones, or at least create new reference types that have cleanup or destructor semantics. You can do things like, you can create data value references, and those act as references to a sort of dumb container of values of a particular type. But there's no way to say, create a DVR, and when this DVR is deleted, also do this other thing. There's no way of associating a destructor with with DVRs of a particular type. But with Rebar, there's not really anything special about types that have destructors. A destructor is just another method, one that the compiler knows to insert a call to at the right place. And ownership is not something that applies solely to things I described, like basically operating system resources. It applies equally to all types, whether they are what G would consider by value or by reference. That distinction doesn't really exist in Rebar, and so it's possible to say that whatever resources a type is or is not holding on to, while values of it exist, they can be cleaned up, or nothing can happen at the end of each variable's lifetime as appropriate. So sort of the point of Rebar is to be a language where you could be the one who implements the file type, or the device handle type, or whatever, something that needs to be cleaned up safely in order to be used safely. Okay, so ownership is the first category of safety guarantee that we get from Rebar. So now let's look at the second one, which is reference safety. So Steve kind of mentioned that you didn't know what race conditions were, and then he looked them up. I'm going to talk a little bit about race condition prevention. A race condition is where you have the ability to make a modification to the same thing from 2 or more places in parallel, such that whatever you do in parallel is going to result in some sort of inconsistent state. And the LabVIEW compiler and the runtime are going to try to prevent you from doing this in 2 different ways, depending on what kind of type of value you're talking about. For by-value types, the compiler will attempt to reorder the things that you're doing with a value that you've forked and are using in parallel, so that whatever would modify the value goes last. So if all the reads to the value happen and then all the writes, or just one write, then that's safe. It also will attempt to take and use subsets or slices of certain types, like arrays and strings, and as long as you're not overlapping your usage, or as long as you're only reading from different subsets of a value, then it will be able to prevent creating a copy. But in any case, what the compiler has to fall back on is creating copies of your data that you use in parallel, so that the usages in parallel are safe. When it can't guarantee statically that you're not doing something that would involve a race condition, it just says, okay, I'm going to create a copy. And that specifically means a deep copy. So if your value is an array holding on to classes which hold on to other things, then everything down the tree is going to get copied. And then for by reference types, one of the points of by references is that when you pass around and branch and copy references, you're not copying the underlying data. And typically there is no way of directly copying the underlying data in a reference type. On the other hand, the runtime is what's responsible for saying, every time we try to access a particular refnum value, we will generally have to lock some kind of mutex in order to access the underlying data. And that means there has to be a mutex allocated for every reference, and also it may be potentially expensive, or the mutex may be contended. So Rebar, like Rust, will allow you to directly create references to specific allocations. And in this context, what a reference is basically just a pointer. At runtime, it's treated as a raw pointer. And this is a little bit contrived, but it's an example of syntax you might use to say, create a reference to something and then use it in place. So this is equivalent to our previous example, where we're adding and multiplying numbers. But what we've done is, for each operation, we've said, okay, take one of these values into an ampersand node, which is what creates a reference. What comes out is a reference back to the variable that was on the input wire, and then do something with it, with the reference value. And then later, on the other side of the structure, there's a node with a curly brace, which represents the point where the reference is no longer valid, where we're giving it up. And so what comes out of that is a wire that represents whatever the original value was. And here with references too, we have a border around the wire that kind of indicates what kind of reference it is. It's a lighter color gray. Oh wow, it doesn't even really show up there. Okay. It is a lighter color gray than the one for non-reference types. And again, there's a series of diagonal hashes to indicate that it's a mutable reference. And so the Rust and Rebar also allow you to distinguish between mutable and immutable references in the type system. And the difference is basically what you would expect. A mutable reference allows you to reach in and modify whatever data is being pointed at, whereas an immutable reference is one from which you can only read the reference data. But there's an additional rule that goes along with this in order to enforce reference safety, and this is sort of shorthanded as mutable XOR aliased. In other words, you can have a reference that is mutable, or you can have more than one reference to the same object at the same time, but not both. If you have more than one reference to the same object at the same time, all of those references must be immutable. And if you have one mutable reference, then that means you cannot have any other references at all to the same object. And the purpose of this is to prevent race conditions, because if you've guaranteed that at any given time you have at most one mutable reference to an object, then anything you do through that reference must be safe. Nothing else can be trying to modify or even read from the same object at the same time, so there's no race conditions. And kind of the way that, the basic way that the compiler prevents you from incorrectly creating aliased mutable references is by preventing wire branches in certain cases. So on the left side here we have a wire inside the structure that is an immutable reference and it's branched, and there's no error, and that's fine because all we're going to be doing with that reference is just reading a value. But on the right, the reference coming out or into the structure is mutable, and because we branched it and we're trying to modify it in two different places at the same time, the compiler flags an error that says the type of this wire is not something that is allowed to branch. And so just by that sort of simple expedient of saying some wires aren't allowed to branch, we've eliminated effectively a large category of problems that you would have normally by passing around what are effectively raw pointers. Okay, so in the abstract for this talk, I talked a little bit about how Rebar was going to help us write performant code. So I want to talk a little bit about performance. I've already kind of mentioned how the G compiler will try to reorder things and to try to prevent copies in some cases. I mean, a major consideration in improving the performance of G code is eliminating the places where it performs data copies. And two of the main tools for doing that are, one, when you have a large value that you know you're going to be sharing or using in a lot of different places or making modifications in parallel that you don't want to copy, you can put that value into a data value reference and then pass around that reference. And a data value reference, of course, is a container for a value that always gets allocated on the heap rather than associated with any one VI because, of course, it can be shared. And then, of course, to get at the value in the data value reference, you have to use the in-place element structure, which has a pair of nodes for saying read and write referenced value. And the in-place element structure is also, in general, a way for saying if I have a value that I just want to make some in-place modification to and then pass the same thing back out, as long as within the structure you're still sort of obeying the rules of in-placeness, you can tell the compiler, treat these two things as the same and try not to copy them. And also the parallel for loop in another way is sort of a way of reusing a large value in place, because the point of a parallel for loop is to say, I want to take this loop and then run n copies of it in parallel. And if what that loop is doing is operating on some array, then really what you want it to do is to subdivide that array into n different pieces that are non-overlapping so that it is safe to operate on all of them in parallel. And that's what the compiler does, behind the scenes is, once you tell it how many copies of the array you want, it will do the work of subdividing any array inputs and then ensuring that they're not copied because you're using subsets of them in parallel. But the main point I want to make is that all of these things you're doing are more hints to the compiler, and that the compiler is running an optimization pass in order to try to give you better memory performance. There are no guarantees, because an optimization, like all compiler optimizations, have to preserve safety. That is, they have to work within the rules of the language, and they have to work within preserving whatever it was that what your program originally said. And so what it will try to do is eliminate copies up to the point where doing so would change your behavior or make it unsafe. With Rebar, instead, the aim is to provide guarantees about memory usage within the type system itself. And so this is kind of the point of saying, we talk about wires as variables and about creating references, because they tend to a language where using things in place and referencing or modifying them in place is the default. And that in order to create expensive copies, you have to be explicit that you want to do so. In particular, what what a wire branch means in Rebar is always that you are creating independent variables for each of the sinks of the branch, and that you are shallow copying the value from the source into each one of those sinks, which is only allowed if shallow copying the type on that wire is safe to do. So for simple types like numbers and for immutable references, it's safe and simple to shallow copy a variable into different places. But for things that, anything that has a destructor, like a file handle, or anything that represents a dynamic allocation into the heap, it's generally not safe or possible to shallow copy the top level thing holding on to it. And so if you want copies of it, that's when you have to be explicit. It also leads to a language where the tendency is for functions to take or to pass through their inputs as references rather than as non-reference values. And typically the only time you would take a non-reference input for a function is if what you're doing actually needs to consume that input or to take ownership of it away from the caller, because that's what happens. When you call something that isn't a reference, you are moving whatever value you had before into the function, and the caller, as a result, no longer has access to it. So all of these things are to sort of lead you towards greater control over what allocations you're making and when, and sort of preventing you from doing things that are expensive but hidden costs. Okay, so I've talked about the safety guarantees, and I've talked a little bit about performance. I want to now talk about a little bit a facility that most programming languages provide you at a basic level, which is the ability to do something more than once, or to control flow through looping. Just to review quickly, there are two basic loops in LabVIEW, and there are other loops, but I'm not going to get into those. There's the for loop in G, and then the while loop, and they have slightly different characteristics because they're used for slightly different things. The for loop is controlled either with an iteration count or a stop condition, which means that it can run 0 or more times, whereas the while loop can only be controlled through the stop condition, and since the stop condition is inside the loop, the while loop has to run at least once. So other languages call this a do-while loop. Both loops support shift registers, which are for carrying values across iterations and into and out of a loop. And both loops also support auto-indexing tunnels, which are a way of feeding an array into a loop and then getting one element of the array per iteration. And here, too, there's a slightly different behavior because a for loop will allow an auto-indexing tunnel to stop the loop. In other words, if any of the arrays you're indexing through run out of values, or you hit the end, then that will stop the loop, regardless of what the iteration count was. But with a while loop, that won't happen. If you hit the end of a loop, and it will just output a default value for the element and then keep going. Rebar only has one kind of loop, and it combines some aspects of both of these. So first of all, to control a loop in Rebar, there's a condition variable, and the variable is identified by sort of the arrow node at the left. It can be initialized. It defaults to true because generally you want to at least run the loop at least once. But if you initialize it to false, then you get a loop that runs 0 times. So like the for loop in G, it can run 0 or more times. And then within the loop, you can modify the value of the condition variable by reference, such as, for instance, assigning false to it, and that's how you would stop the loop by the condition variable. Instead of shift registers, loops in Rebar allow you to borrow values mutably within them. So there's a similar ampersand node here, which says, okay, within this loop, there's going to be a mutable reference to some value, which means that you can reassign to it more than once, actually, inside the loop. And this stands in for the function of being able to carry values across iterations and into and out of the loop. And then instead of the auto-index tunnel, there's a more general substitute called the iterate tunnel. And what the iterate tunnel does is it takes an object that implements a trait called iterator, and I'll say more about that in a second, and says, for each iteration of the loop, I will get one more value from this iterator, the next value from the iterator, and then once the iterator is done, I'll stop the loop. So behaves similarly to the auto-indexing tunnel in the for loop, except that it can work on more than just arrays. So an iterator is essentially an interface or a trait that describes an object that has a method that lets you get a next value. That is, it takes the iterator itself by reference, by mutable reference, in fact, and it modifies the iterator in some way and says, give me either the next value in the sequence or give me nothing if the sequence is over and there's nothing left. So a simple example of that is if we take just a range value, that is, some number up to some other higher number, and we create an iterator from that, the iterator can have a pointer or just a current value and a high value, and on each iteration of the loop, when we tell it, give us the next value, it'll just increment the value and say, if we haven't hit our limit yet, then that's the next value. And if we take a range from 0 to n, then that substitutes for the iteration count node on the for loop, because that's essentially what you would be doing in G with the for loop, is saying, run this loop n times. But it can also work a little bit more generally than that, because you don't have to start at 0. You can start at any number and go to any higher number and loop over that range directly, rather than having to start with 0 and transform the iteration value somehow. Okay, so a slightly more complicated example is, let's say we want to do something we have a file, and we want to do something with each of the lines in that file. So, normally in G, we would say, okay, open the file, and then within a loop, let's, read another line from the file, and if that didn't result in an error like end the file, then do something with the line, otherwise tell the loop to stop. Here, what we can do is say, take the file handle and put it into a file line iterator. And the purpose of the iterator is every time we ask for the next value, it's going to read a new line from the file. So within the loop, we can just focus on whatever it is what we wanted to do with the line. And in this case, we're just taking all the lines and appending them into one long string. But you can imagine doing other things like counting them or pattern matching them or transforming them in some way. But the point is, we've separated what it is we want to do with the sequence from the logic of generating the sequence itself. That part is encapsulated in the iterator and in the single node syntax that allows us to get all of the values in this iterator one at a time. And so that's kind of what we can think of an iterator as, is sort of like a pump of values that we can, we can cycle through and say, give me these things one at a time. And you can kind of think of this from one of two directions. Either an iterator is something that continually does some specific thing, like reading a file line or pulling bytes off of a network stream or pulling frames out of a device or something, and then it's producing a sequence of values from that action until it's no longer possible to do. Or you can think of an iterator as something that can be observed, something that continually produces events or values, something that can be watched. And this would be something more like if you have a queue that somebody else is putting things into asynchronously, or if you have control events, or I guess user events would be another analogy. It's something that you can observe and get pull things out of one at a time. But the nice thing about having an interface or a trait for iterator is that it allows us to do more things with the iterator itself than just loop through it. The iterator itself can be transformed in some way. So a really simple example of this is if you have an iterator and you just want the first n elements of it, or if you want to skip the first n elements of it, then there's a simple function to do that, and you just get out another iterator that represents the transformation, which is either the first n or the last n. You can also take some function and apply it to each of the elements in the iterator in order to transform it in some way. So if your function returns true or false, you can have a new iterator that says, give me only the things in this other iterator that return true for some function, which is filter. Or you can have a function that says, transform these kinds of values into these other kinds of values, and that's a more general way of mapping or selecting your iterator. And you can also you can combine multiple iterators through ways like wait for each thing in a set of iterators and then combine each of those into an aggregate, and then create a new iterator of the aggregate elements. Or you can multiplex them such that you take one from one and then one from the other and create an interleaved stream of iterator events. These are all things that you can do on iterator objects themselves in a generic way without having to explicitly loop through the iterators. And the last point I want to make is that all of this is built on what's inherently a sequential operation, which is saying I have a linear sequence of values that I want to get. And the abstraction is to say, okay, there's an object that knows how to produce that sequence, and it is continually modifying itself in order to produce the values of that sequence. But that in turn requires that doing that modification is going to be safe, that we're not going to try to modify the iterator more than once in parallel, and that we'll be able to clean up the iterator when it's done. So we've taken the guarantees of that ownership gives us and that safe references give us for preventing leaks, use after free, and race conditions, and we built on them this concept of an object that neatly encapsulates a stream of values. Okay, so just to wrap up, so what Rebar is a graphical data flow language that looks like G but acts somewhat differently, and it pulls in these concepts of ownership and reference safety from Rust. It does that by representing variables or containers of values as wires, as sequences of wires that have defined start and end points. And it implicitly tends to use things in place and to reuse things by reference, and requires that you do things that would be expensive, like copying explicitly. And then it builds on these to enable simple, powerful value stream types that are called iterators. So there's the GitHub link again, and I would like to know what you think. I'll be here for the rest of the conference, and yeah, that's it. Let's go to lunch.